My name is Asger Sellerup Jensen. I'm the head of quantum at NKT Photonics. What we're showing on the table today is our variety of Koheras HARMONIK systems. It's a mixture of fiber lasers, fiber amplifiers, and frequency conversion modules that allows us to address almost all wavelengths in the visible spectrum used in quantum applications. So specifically, these lasers are used for quantum computing applications, typically those involving trapped atoms or ions, where high power, low noise, narrow line width, and high level of reliability is required. So fiber lasers themselves have some inherent properties that makes them an attractive choice for lasers in quantum. Problem with fiber lasers is that typically don't have the right wavelengths. This is what we solve with the harmonic systems. Fiber lasers themselves are very attractive for basically any application where you need low noise, high level of reliability, very little service, very short setup time. And it comes about because fiber lasers themselves are just a very robust platform to build a laser on. And robustness in lasers translates to very attractive laser properties or light properties as well, such as very low phase noise, very low intensity noise. And since all of this is coming out of a single mode fiber, you also have all the most attractive beam qualities built into the system itself. Fiber lasers come at infrared wavelengths, which is why they are typically not attractive for quantum experiments, which typically have their target wavelengths in the visible part of the spectrum. This we solve with frequency conversion modules like the one you see here, where we mix and match different types of frequency conversion to address the wavelengths that are required in the applications. This allows you to use the fiber laser properties at visible wavelengths and allow you to do all the complicated modulation that just works a lot better in the infrared. Do that before the frequency conversion, so you don't have to deal with locking in visible wavelengths. You can lock in the infrared. You can do all the frequency shifting, amplitude modulation, all of that stuff you can do where it's nice and comfortable at the infrared wavelengths. So another aspect of fiber lasers is that fibers allow you to scale the power to very, very high powers compared to other laser platforms. And this is something that's very inherent in fiber lasers. Fibers themselves has a very high surface to volume ratio, and when you amplify power in a fiber, it allows you to extract the surplus heat that's generated in the amplification process very, very efficiently. And since the interaction length is very long in a fiber compared to, say, a crystal or a tapered amplifier, the heat is also distributed over a much longer volume, which allows you, again, to manage heat a lot more efficiently. So you can amplify the optical powers to very high powers before you run into the typical limitation of power amplification. So in the future, where stuff like number of qubits comes to a point where the laser powers required to run them becomes exceedingly high, fiber lasers is going to play a key role because no other laser platform can scale to the same power levels. So what we are showing here today is the different modules that make up a quantum laser. Our approach involves three major steps, which is the generation of the pristine light that you want to use in your application. This is generated in our DFB fiber laser, which is a very low noise, low power laser platform that will output a light mode hop free for thousands of hours, no problem. This comes at low power, so in order to get it to a useful power level, we amplify it in our Koheras boostic amplifier platform. So this is a simple taking a fiber and connecting it to the amplifier platform, and out comes high power single mode light. In order to make this light useful, we need to frequency convert it to an appropriate wavelength. This is done on our harmonic conversion platform, which is a highly efficient frequency conversion platform. We do this not necessarily in one step. We have second harmonic generation modules, some frequency, and different frequency generation platforms. And because we have so much power from the get-go, this allows us to combine these systems So a second harmonic generation system can feed its output light into a, in this case, a some frequency module, where it can get combined with another line of light, which is the modularity that allows us to ultimately address all the visible wavelengths with just a few infrared wavelengths. And finally, the output power of these can be very high. We are talking several watts, up to 10 watts. And of course, that doesn't lend itself very nicely to being fiber delivered, which is, for convenience, often very important. But at NKT Photonics, we have our photonic crystal fiber platform that allows us to make single mode, truly single mode fibers at all wavelengths that can handle even these very high powers, which it would otherwise be impossible in just standard fibers. So the new kid on the block at NKT Photonics is this thing here. This is our Adjustic T20. And what's new about this is that we've so far been using fiber lasers in the ytterbium range around 1 micrometer, the erbium range around 1.5 micrometers. But with this, we are opening up the whole thulium range around 2 micrometers as well. Our first product in this line is our T20 at 1762, which is a wavelength that's specifically chosen for those who do experiments with barium ions, where this is a key and often very hard wavelength to come by in a reasonable quality. Here we supply a solution where you get all the benefits of fiber lasers at this very challenging wavelength.